So I have a question for you guys. Let's imagine a perfectly plastic material for a second. So if I just do a tensile test, so talking about sigma 1,1, and we'll use the simplest assumption that after the yield point, which we'll call y, the material just behaves linearly, so perfectly plastic. That's what this is called, perfectly plastic. So as an aside, before we go forward, I'm going to ask you guys a question. Let's imagine that I'm loading, I have a complex loading. So I have a little cube of material, and I apply some forces to the exterior of it such that I measure the stress, and sigma 1,1 is 10 megapascal, and sigma 2,2 is 20 megapascal. And my yield stress is 15 megapascal. So the question is then, is the material yielding? So everything I've looked at over here is just one-dimensional. It wasn't a complex loading scenario, right? So if it's just one-dimensional and I only have one stress, right? So if I only have sigma 1,1 and it's 10 megapascal, and y, which is the yield point, is 15 megapascal, and I ask you the question, is the material yielding? What's your answer? So if it's just one-dimensional, and I'm pulling on it at 10 megapascal, and the yield stress is 15 megapascal, is it yielding? No. Okay. What if it's one-dimensional and I'm pulling on it at 20 megapascal, and the yield strength is 15 megapascal? Is it yielding? Yes. Okay. But what about this scenario where I have a complex loading? Is the material yielding? So this, you don't know. You don't know because you don't have a proper model to determine if it's yielding or not. And so that's sort of what we're going to set out to do here. Okay. So now let's return to our one-dimensional yield stress. And I'm going to write down the stress tensor for this scenario, the whole tensor. Right? So the whole tensor is sigma 1,1, 0, 0, 0, 0, 0, 0, 0, 0. So this is a case of uniaxial stress. So the stress is homogeneous in the 1,1 direction. Okay. So let's examine the case right at the moment of yielding. Right. So when sigma 1,1, so clearly sigma 1,1 is equal to E, the Young's modulus, times E11 when it's elastic, and then when it's plastic, so this is for the elastic case, and then when it's plastic, it's equal to Y. And since it's perfectly plastic, it's always equal to Y. In other words, you know, if we follow the stress strain curve, if I load it up, if I increase the strain, I'm elastic, I'm elastic, I'm elastic. As soon as I cross that point, I'm plastic, meaning I'll continue to increase the strain, but the stress never increases past Y. Right? I'm always just at the stress Y. Right? So right at the instant of yielding, let's write down what the deviatoric stress is. Right? So remember, the deviatoric stress is the stress tensor minus 1/3 sigma kk sigma ij. Right? So So let's write down what that is, right at the instant of yielding. So I have y 0, 0, 0, 0, 0, 0, 0, 0, 0, minus y over 3, 0, 0, 0, y over 3, 0, 0, 0, y over 3. Right? And so that's equal to 2/3 y 0, 0, 0 minus 1/3 y 0, 0, 0 minus 1/3 y. All right, so that's the deviatoric stress right at the instant of yielding. Okay? And remember what I said about, we're talking about metals plasticity. The plasticity is isochoric, without volume change, which means that the hydrostatic part doesn't contribute to any plasticity. Right? So our assumption is that the only thing that contributes to plasticity is the deviatoric part, okay, Sij, some function of Sij. Right? So what we're going to do then, we're going to define something called the equivalent stress, okay? And it's a scalar value, and we're going to define it to be the square root of 3j2. And what is j2? 1/2 Sij, right? So another way to write this would be that it's 3/2 Sij, Sij, right? And so this is Sij. So if we do the contraction and divide by or multiply by 3/2, what you'll see is that this becomes y. So if I compute 3/2 Sij, Sij, where this is Sij, what I get is y. And so what we did was we defined this equivalent stress, and that's where the sort of square root of 3 comes from. We defined this equivalent stress to be equal to y, the yield value, a scalar value, okay? Okay? Because if we don't put the square root of 3 there and you just use 1/2 Sij, Sij, then you have a 1 over the square root of 3 thing that's there, and we don't like that. But just want it to be equal to the yield stress. So the equivalent stress is a scalar value that's equivalent to the yield stress, and we define it like this. Okay? And so sometimes that equivalent stress is also called, sometimes it's also known as the mean stress or the von Mises stress. And so then what we're going to talk about here is something called von Mises plasticity. And another name for it would be J2 plasticity. And so in von Mises plasticity, we have an assumption that under a triaxial stress state, this is our complicated stress state, under a triaxial stress state, the material is yielding. That means it is plastic when the equivalent stress, or the von Mises stress, is greater than or equal to y. So this gives us a way to answer that question I posed. So the equivalent stress again, is square root of 3J2. But another way to write that in terms of all the stress components is 1/2 And so if we go back to our problem and we plug in these values, sigma 1,1 is 10 megapascal, sigma 2,2 equal to sigma 3,3 equals to 20 megapascal. We plug those guys in there and compute what the equivalent stress is going to be. It's going to be 10 megapascal. And our yield stress was 15, therefore not yielding in this case. So a lot of times, so this is our plasticity model. This is it's a model that we develop to determine if the material is yielding or not. And so a lot of what we'll do is we'll define something called a yield function. So it's a function of the stress. And in the case of J2 or von Mises plasticity, we say that it's the square root of 3J2 minus y. And strictly, this always has to be sort of less than or equal to 0, right? So you can have a test that says if this function is less than 0, then your material is elastic. And if this is equal to 0, then it's plastic. And it can actually never be greater than 0 because if you remember in this case for perfect plasticity, greater than 0 would imply that you're out here somewhere, right? So the stress is either elastic or it's on that line because stress is all in a perfect plasticity model. Stress is always y once it's yielding. And so one way to visualize this would be in principal stress space. So this is sigma 1, sigma 2, sigma 3. So I'm looking right down the axis. The sigma 1 equals sigma 2 equals sigma 3 axis. We're looking right down it. Then this would be a circle. Sorry, that's not a very good circle. But the radius of that circle would have radius square root of 3J2, or y. So if you were to compute the principal stresses and find out where you're at in this space, you're either going to be inside the circle, in which case you're elastic, or you're going to be on the surface of the circle, in which case you're plastic. So just, if it's not clear what I'm drawing there, like in this is sigma 1, sigma 2, sigma 3. This is the line. Sigma 1 equals sigma 2 equals sigma 3. And we have a sort of a cylinder that's infinite in both directions. And the radius of that cylinder is square root of 3J2. So over here, it's like we're sitting on this line looking down it this way. And it's infinite because the line sigma 1 equals sigma 2 equals sigma 3 is the pressure, right? That's the hydrostatic component. And what did I say? Plasticity. So if I just have the material and I just squeeze it even to infinity, but in a hydrostatic way. If I squeeze it on all sides all the way to infinity, I'll never plastically deform a metal that way. Right? If I let it go, the metal will always pop back where it was. Okay? And so I think you can probably see where one of the modifications is for rocks. Right? That's what I said is not true about a rock. Right? If I squeeze a rock hydrostatically, eventually I'm going to collapse the pores, and when I let it go, it's not going to pop back. Right? It'll pop back some, but the pore collapse is going to be permanent. Right? So it may be a little bit hard to understand what's going on, but this will all come full circle. At the end of the class, I mean, we will actually code up a plasticity model or part of one, and you'll actually get to see how this all works. So the idea that how these models work. You test to see if you're elastic or plastic. If you're elastic, you just apply Hooke's law and go to the next step. If you're plastic, you have to do something special, right? You sort of, because what happens is the way you test is usually you take what's called a trial step. So you take a step, a load step, as if it's purely elastic. And then you compute the yield function and you find out, am I inside or am I outside? And if I'm inside, it's just elastic. You accept the trial step and you go on and you move on. But if you're outside, that means you're plastic, but you're in fact in violation of the constraint that you have to be on the yield surface, right? So you can't actually be out here. You're either inside or you're on it. And so if you take a trial step and you find yourself outside of it, then you have to return yourself to the yield surface. So this is actually what we'll talk about next time, a simple return algorithm called a radial return. So we'll talk about how you compute actually to get yourself back on the yield surface, right? And so sort of all theory at this point, but at the end of the class you'll get to code this up and see how it works, which for me, I never understood any of this stuff until I started coding it. So I think that's when you really understand it.